Everyone, my name is Dr. Vile. Welcome to my chemistry podcast. The aim of this podcast is to help prepare you for your A-level chemistry exams. And in this particular video, we're starting a series looking at how we draw organic molecules. And this particular video is going to focus on drawing aldehydes, ketones, and carboxylic acids. So we're going to take each of these in turn. And the way I'm going to do it is with lots of examples. So the name of the molecule is going to appear on the screen. If you feel vaguely confident already with how to draw these, pause the video after each one, have a go at drawing it, and then carry on watching the video and see if you got it right. If you have no clue, then hopefully you will by the time you've watched me talk you through it. So let's get cracking. So the first functional group we're going to look at is aldehydes, and I will start off by showing you what the aldehyde functional group looks like, and we'll just work through some examples. So the first name is propanal. Now when you have the name like this, it splits up into two parts of the name. So you've got, if I highlight it here, you've got propan, which means 3 carbons, and then al at the end, which means we've got an aldehyde group. So you start off by drawing a chain of 1, 2, 3 carbons like that. An aldehyde is a carbon double bond to oxygen at the end of a chain, like so. And that's it. An aldehyde has this carbon to oxygen double bond at the end of a chain, and then you add the appropriate number of hydrogens to the rest of your molecule. So the golden rule is that carbon always makes 4 bonds. This carbon at the end is currently making 3, so it needs 1 more to hydrogen. This one here needs 2 more. And then the last one on the left needs 3 more. Like so. And in terms of skeletal formula, common question is to convert this into skeletal formula. You have the carbon backbone as a zigzag, where each point of the zigzag represents a carbon. So this is carbon number 1, then down to number 2, and then up again to number 3. We don't have the hydrogen shown here, and we certainly don't show the carbons. And then the aldehyde group itself, you have a double bond going upwards to the oxygen. Ignore the fact that these are really close at the moment. That's annoying me, but I've just run out of space. Let me put it into a box like this. And then this is one of the hydrogens that we do actually show on the skeletal formula because it's part of the functional group itself. So this is carbon number 1, carbon number 2, carbon number 3 in a zigzag, like so. And because the end point is going upwards, the aldehyde group goes upwards. So that's the skeletal formula. And then we arrive at this one here called phenyl methanal. Well, methanal means 1 carbon with an aldehyde group. Always at the end of a chain. And then phenyl, not to be confused with phenol. Phenyl means a benzene ring. So you have your bond going down, and then we'll draw a hexagon. Now there's 2 ways of drawing the benzene ring. You could show it with the circle in the middle or the single and the double bonds. I'm not going to go into the bonding in benzene in this particular video. I will post one up, but from our purposes I prefer to use the circle, which shows the modern bonding in benzene, but I'll discuss that in a separate video. So phenyl means a benzene ring, methan means then 1 carbon in the chain, and then al means an aldehyde. Let's carry 2-methyl butanal. So we break the name down into chunks again. Butanal, let's draw that first. 1, 2, 3, 4. Aldehyde group at the end. Now you might be wondering, why am I drawing the aldehyde group at the right hand side rather than the left hand side? Doesn't matter, basically. It doesn't matter. However, when we number the methyl group that's coming off carbon number 2, that does matter because the aldehyde group counts as carbon number 1, so therefore this becomes carbon number 2, and you need to have a methyl group coming off it. And a methyl group is just going to be a CH3 group. and then you add your remaining hydrogens to the molecule. Now I've deliberately picked quite small molecules here to illustrate these just because they're a bit quicker to draw. Remember, you'll need to be able to apply these naming principles to whatever the question asks you. Okay, so that's 2-methylbutanal. If it was 3-methylbutanal, then the methyl group would be coming off the third carbon. So we always start the counting at the aldehyde group. So 1, 2, 3, 4. In terms of skeletal formula, draw out your zigzag with 4 points, aldehyde group at the end, and then your methyl group coming down off carbon number 2. And then lastly for aldehydes, I've got butanediol. Now butanediol, butan means 4. I'm just going to draw the displayed formula here because it'll get messy in the space that's available. So 1, 2, 3, 4. Dial, di means 2. So dialdehyde. So you need an aldehyde group at each end of the chain, like so. They can only be at the end of the chain because that's what an aldehyde group is. So we don't even have to bother numbering the position of the aldehyde group here. It has to be at the end, and then you just put your remaining hydrogens on so that every carbon is making 4 bonds. You'll have to excuse the messiness of my hydrogens here. I'm just using my mouse. But I think it's clear enough. So that's aldehydes. I hope that's helpful. Let's move on to ketones. Now, a ketone is very closely related to an aldehyde in that it has a carbon to oxygen double bond. But with a ketone, the carbon to oxygen double bond has to be somewhere in the middle of the chain. Now, I don't mean symmetrically in the middle. I just mean not at the end. So propanone, prop means 3. 1, 2, 3. And if it's got a carbon to oxygen double bond that's not at the end, it has to be on the middle carbon here. And then just to save time, I'm just going to call these CH3 groups. Skeletal formula, you would draw propane, which is just this zigzag, and then you have the double bond to the oxygen going up, like so. Butanone, but means 4, so 1, 2, 3, 4. Now you've got a choice here. It can either go on this carbon here, carbon number 2, or carbon number 3. Actually, that's the same thing, depending on whether you count from left to right. So it doesn't matter where I put it here, it would equate to the same thing. So I'm just going to put it here, and then just turn each carbon so it's making the appropriate number of bonds to hydrogens. This becomes CH2, and this becomes CH3. And skeletal formula, draw out butane, but then have the double bond to oxygen coming in there. Okay, so with pentan-2-one and pentan-3-one, I'm just going to stick to the skeletal formula, and I'm going to show you how this works. So just draw out pentane first. 1, 2, 3, 4, 5, and I'll draw it out over here. 1, 2, 3, 4, 5. Now for pentan-2-one, let's do the numbering. Carbon number 1, carbon number 2. It doesn't matter if you go left to right or right to left. 1, 2, 3, 4, 5. We always go in the way that would give us the lowest possible numbering system. So pentan-2-one would have the double bond on carbon number 2, and pentan-3-one has the ketone group on carbon number 3. Notice where the bonds are meeting and they are going upwards, like in pentan-2-one, the ketone group goes upwards, but whereas the bonds on pentan-3-one are going downwards, so the ketone group goes downwards. It's just by convention, it looks neater. Okay, so that's pentan-2-one and pentan-3-one. Okay, we're going to move on to carboxylic acid group. Now, I'm just going to focus on the displayed formula. So when you have a carboxylic acid group, you have a carbon double bond to oxygen, and then coming off the same carbon, you have a single bond to oxygen, which is bonded to a hydrogen group. Not a hydrogen group, a hydrogen atom. So C double bond O, and then a single bond to OH. And that's the oic acid bit of the name. And then the other half is ethan, which means 2 carbons. So it's 2 carbons here with the carboxylic acid group on it. And if you've got propanoic acid, you'd have 1, 2, 3, double bond to O, to OH, and then just stick your remaining hydrogens on to make sure that each carbon is making 4 bonds. Really important that we get this bit right. The amount of times on an exam that students have carbons making 5 bonds or 3 bonds, no, carbon always makes 4 bonds. And when you're naming carboxylic acid, remember the name splits up into 2. You've got the oic acid that refers to a carboxylic acid, and then the number of carbons is given beforehand in the previous bit of the name. And then 2 more examples just to finish the video. I don't know why it says ketones there. Let's cross that out. These are obviously carboxylic acids. So butandioic acid to start off with. Well, butan means 4, so 1, 2, 3, 4, and then so that's the butan bit. And then dioic acid means 2 lots of carboxylic acid. Now, a carboxylic acid has to be at the end of a chain. So you'd have the carboxylic acid at the right-hand end of the chain, and then a carboxylic acid at the left-hand end of the chain as well. Notice that the bond is always going to the oxygen here, not to the hydrogen. That's really important. And then these would be CH2 groups. By the way, don't do it like this. If it asks for full displayed formula, make sure you show every bond. And then just to finish, 2-methyl-butanoic acid. So butanoic acid means 4, so 1, 2, 3, 4. Draw your carboxylic acid group at the end. Could be the left-hand side if you want to. Just going to tidy that up a second. That bond there looks a bit skewy. So the carbon of the carboxylic acid counts as number 1, in the same way the carbon of the aldehyde was number 1, and therefore this second one is carbon number 2, so you'd have a CH3 group, which is your methyl group, coming off carbon number 2, and then just stick your remaining hydrogens on. Anyway, I hope that was helpful for you in terms of naming aldehydes, ketones and carboxylic. If you found the video helpful, please like it, please subscribe to the channel, please share it with your friends, and I will see you on the next video.